Today we talk about what is one of the most fundamental results in really all of science, not just physics, the conservation of energy. Recall that the external work is what changes the energy state of a system. The total energy before plus the work is the total energy after. Here I'm going to follow the convention of the textbook author Knight, and somewhat unusual, we keep the change in thermal energy intact rather than splitting it into a before and after. The reasoning behind that is that we rarely know the starting or ending values of E thermal, but we can usually measure its change. So we have the initial kinetic energy plus the initial gravitational energy plus the spring energy plus any external work equals the final kinetic energy plus the final gravitational energy plus the final spring energy plus whatever the thermal energy has changed by. It is often convenient to consider an isolated system on which no work is done and to which no heat can flow. In that case, the total external work is zero, so we have the law of conservation of energy, that the kinetic energy plus at the start plus the gravitational energy at the start plus spring energy at the start equals the final kinetic energy plus the final gravitational energy plus the final spring energy plus anything that's been turned into heat inside the system. In an isolated system, the energy can be transferred from one form to the other, but the total will not change. The ultimate isolated system is the universe itself, of course, since by definition there's nothing outside of it. Therefore, in the universe as a whole, the total energy must remain constant, which is often phrased as energy can be neither created nor destroyed, but only transformed. Imogen tries her hand at the ring the bell game at the carnival. She knows that the bell is 3 meters above the bottom, and that she can swing her mallet to give the ball an initial speed of 8 meters per second. Will she succeed? Let's start off by considering the before moment to be just after she hits the ball, and the after moment to be just the moment the ball is at its maximum height. First, let's construct the isolated system. So move the numbered icons either into or out of the system. We know we want the Earth in the system because we want that obviously to have the gravitational effect. And we want the ball because that's the thing that's moving. But we'd rather leave things like Imogen and the bell and the mallet outside because we don't know anything about their energy states and they don't interact in this case. So we don't need to have, they're not doing work on the system. Once she's hit the ball, this is really important, she's not doing work or anything, and so this is a simple enough system to analyze. And now we can go back to our original question, which is, will she succeed? So, figure it out. Will she succeed? One approach we could take is find the kinetic energy of the ball when it reaches the bell. So we go through and we say, well, the kinetic energy before plus gravitational energy before plus the spring energy before. So 1/2 mvi squared, but these two are 0 because we'll take our gravitational point to be 0 where she launches the ball. And there is no spring, so of course the spring energy is 0. And then after, since there's no external work anymore, why is there no external work? Because the Earth is inside our system, so it's not doing external work. Even though gravity is doing work on the ball and so on, it's not external, so we can ignore it. And so we end up after with just the kinetic energy at the end, plus gravitational energy end, plus the spring energy at the end, plus the change in thermal energies. We know that we will not significantly heat the ball as it goes up. Maybe a little bit, but probably not significantly. And so we have 1/2 mvi squared equals kf plus mgh, and we can figure out that the final kinetic energy is 2.6 joules per kilogram times whatever the mass of the ball is. We weren't given the mass of the ball, so we don't know the actual kinetic energy, but we know that this whole thing is positive. So the situation is possible, which means that the thing will have reached that height. You might imagine if this was like a clay ball and so on, that we could actually add some heat to that, but it'd be a special case. It wouldn't be what we were seeing here. A spring-loaded gun shoots a plastic ball with a launch speed of 2.0 meters per second. If we were to compress the spring twice as far, then the ball's new launch speed would be which of these? All right, let's keep some things in mind. The spring energy in general is 1/2 kx squared. So if we have originally US 0, then the new spring energy is 1/2 k twice that distance squared, 1/2 k times 4x squared, which is 4 times 1/2 kx squared, or 4 times the original, sorry, that was pretty bad, 4 times the original spring energy. But we also know that the spring energy becomes the kinetic energy. So our new kinetic energy is 4 times the original kinetic energy. But we also know that kinetic energy is 1/2 mv squared. So if I have a factor of 4 here, I must have a factor of 2 squared there. So it's a factor of 2. It had been at 2, it must be at 4. Same kind of problem. Spring-loaded gun shoots a plastic ball with a launch speed of 2 meters per second. If the spring is replaced with a new spring having twice the spring constant, but is still compressed the same distance, what happens to the launch speed? Well, now we know that the new spring energy is only twice the original spring energy, which means that the new kinetic energy is only twice the original kinetic energy. And so we might look at it this way. We have a square root of 2 factor, basically, but we would say that 1/2 mv squared is twice 1/2 mv0 squared. Cancel the m's, cancel the halves. We have v squared is 2v0 squared. V is square root of 2 times v0. Square root of 2 is about 1.4. Twice 1.4 is just about 2.8.